everybody. Today I'm going to talk about a paper that I've been working on for the last few years. It's kind of in the final stages of editing at this point. And it's going over kind of as a follow-up to what my colleague Chris Galley has been doing with the inversion modeling of gravity and looking at MOHO depth and trying to see what all of the geological evidence there is beyond looking at the VMS deposits for the extensional architecture in the early extensional architecture in the Abitibi. So just to give you some kind of context on my background and my bias, my comfort zone is in modern rift systems and plume environments and kind of looking at those from multiple different perspectives. And so I was tasked with taking that knowledge of what we know about what happens in modern settings within rifts and applying that to an Archean environment. And so we all know in the Abitibi, as Tom just highlighted in his talk, that the VMS deposits are not equally distributed in the Abitibi, neither spatially nor temporally. And so it's, fairly well established, the connection between VMS deposits and extension. We know that in modern settings, the analog of C4 massive sulfide deposits are very strongly associated with extension. And so what we wanted to address is where exactly are those extensional centers? It's not a new concept that we probably had a rift in the northern volcanic zone and a rift in the southern volcanic zone, but what can we pull out about the nature of those extensional environments from the geology as it currently is? And so one way to do that is, look at the locations of the VMS deposits, since they are indicators of extensional environments. But what do we do to connect the dots between where those deposits are? Because they're not spatially, uniform across the belt. And here is just highlighting the age assemblages within the Abitibi, and so really just highlighting that the volcanic rocks and deposits that we have in the north are generally older, and we see this younging towards the south. And then I made this, I don't know if it's going to play, this GIF a few years ago that just kind of shows that construction where we're overlying younger assemblages on each other, and you can, it just helps visualize that southward progression of volcanism. And so just introducing the MOHO depth model again has been presented several times by my colleague Chris, and was this model and the interpretation was published this past fall in Nature Communications. That's the article reference there. And so as I mentioned at the beginning, my job was kind of to look at this MOHO depth model and that we, propose outlines the sort of rough rift architecture in the Abitibi and see what other geological evidence we can look at other than the locations of deposits that would support this rift architecture. And so Chris, highlighted possible locations of multiple different rift segments, and I kind of took that a step further in outlining those anomalies and giving them names. So there are 7 different segments. Most of them trend east-west, which is, as expected. That's pretty much the trend of a lot of the geology in the Abitibi. But one kind of interesting outcome was this prominent northeast-southwest trending boundary, which is oblique to the main fabric of the belt. And so this was a main point of interest for us. I've been referring to it as the Kivalon boundary, but it does extend pretty much all the way from Amos up into Demerayville. And so addressing the nature of that structure was also a point of interest. Here's just a quick slide to highlight. You might see this model and say, okay, well, the shallow MOHO areas are correlated with where the volcanic rocks are. And so this is just to highlight that it showing with different contours of that MOHO depth model, and then sort of the filled areas representing where the volcanic rocks are, that they're actually confined to specific areas. And so you can see main parts of the belt, like that big outcropping of the Stoughton Rockamore assemblage in the central part of the belt, are not associated with a shallow MOHO anomaly. So it doesn't simply reflect the distribution of the volcanic rocks. This is just basic, cartoon of a rift and where, various sort of geological parts of a rift system would be. And so what we tried to think of in order to test this geophysical model is, from what we know in modern rift systems, what kind of geological parameters can we look for that we see and are preserved in the Abitibi that would highlight potential locations of rifts. And so looking at crustal architecture is very important, and so this whole study started with looking at MOHO depth, and so we know rifts are associated with extension and shallowing of the mantle, and then they're also associated with extensional faulting, and so we should expect to see some association with large-scale extensional faulting and these MOHO anomalies. We know that extensional centers are associated with hydrothermal activity, and so in modern extensional systems, the modern analog being seafloor massive sulfides, but then in the ancient realm, VMS-style mineralization, as well as alteration, which is kind of a byproduct of that fluid flow. We also looked at a few different key lithologies, one of which being komatiites, as you heard from the talks by Michael Lesher. These require high heat flow, probably thinner crust areas, some level of crustal permeability to get those very dense melts to the surface. And so if we are in an environment that has rifting, those would likely be the preferred location for those komatiites to erupt. We also looked at the distribution of banded iron formations and kind of lumped in there, but peritic shales as well. Those representing either deposition of chemogenic sediments produced by hydrothermal systems, or possibly more widespread kind of low temperature style hydrothermal systems. And then finally, looking at synvolcanic mafic to ultramafic intrusions. We see an association between centers of rifting and volcanic complexes, and so we should see an association between these MOHO anomalies and those complexes. And so the first thing was just to plot the major structures that we're aware of within the Abitibi on this map of the MOHO. And what we noticed right away is that some of the major structures do seem to follow the edges of these MOHO anomalies. And so the ones that we're all familiar with, for instance, the Porcupine Duster and the Larder Lake Cadillac breaks seem to follow the edges of this anomaly that outlines the Blake River. And then we also have these east-west fault systems in the north that are kind of discontinuous in this area, but seem to form the borders of these MOHO anomalies in the north as well. And so these are obviously very complex deformation zones that have had long polyphase protracted histories. But in terms of their origin, since we know that there was extension, I'm kind of hypothesizing, along with many others, but kind of at the full scale of the belt, that maybe a lot of these major structures originated as the bounding faults of rift systems. That would create major crustal discontinuities that could then very easily focus later deformation. And so that's kind of one of the hypotheses that we're trying to test. So one thing that you may have seen in especially gold prospectivity mapping is looking at complexity of fault systems. And so we wanted to apply that to look more from like a tectonic setting perspective and a rift perspective. Since we know that crustal permeability and that intersection of various fault systems is an important way to focus hydrothermal fluids. And so I compiled a database of faults from OGS and MERN, but as you might be aware, and it makes sense, that the mapping detail is a lot better in areas surrounding the main mining camps. So you'll already get a bias if you try to just look at that data, because if you're trying to look at complexity of faults, they're going to be more complex where the mapping was more complex. And so one way we tried to mitigate this is I undertook this project to do some remote mapping from geophysical data, primarily digital elevation models. There's some great high-resolution LiDAR data for the Abitibi. And so you can see these two data sets. There's a lot of data in here, so it kind of just looks like a bit fuzzy, and like it's all one gray blob, but there is two main data sets. The black outlines are from the surveys, and then the gray lines are what I mapped from the remote sensing data. And so this one caveat, which I'm aware of, this includes faults that we know to be late, as well as faults that we're not so sure, and faults that are probably early. So sort of the key here is this is really representing crustal permeability accumulated over time. And so if we look at a simple measure of the complexity of those fault systems, so just looking at the spatial density, so a heat map of the intersections between faults, this is what you get from those two data sets. And so we're looking at areas where we have the highest amount now of crustal permeability, and we do see hotspots associated with our major areas where we've had VMS mineralization. And so we see a major hotspot in Matagami, around Chibougamau, and then this kind of corridor from Val d'Or all the way to Matheson. Kind of following up from the previous talk on the Swayze, we don't see that same level of fault complexity there. I will note that this area north of Timmins, around Kig Creek, we can't really evaluate it in the same way as the rest of the belt, simply because there's not much outcrop in that area, and so the field mapping data is sparse, and also it's the most glacially modified part of the Abitibi, and so when you're looking at elevation data to try to pick out structures, it's kind of all smooth. So it's unfortunately this area we don't have as much information on. In terms of some of the key lithologies that I've been talking about, this plot is kind of a map where I've just generalized the main groupings of some of these key lithologies, and so it's important to note that, for instance, the komatiites, which are in purple, or simply called them ultramafic volcanic rocks, and the banded iron formations in red, this isn't the true thickness of individual stratigraphic horizons. It's simply a grouping of where those units are spatially dense. And so if we look at the distribution of these with respect to these shallow moho anomalies, the main thing that popped out to me are these symvolcanic mafic and ultramafic complexes. Pretty much all of them, with the exception of Noranda and Blake River, are associated with these central symvolcanic mafic intrusions, which is what we would expect in a rift environment, at least a sort of slower extensional environment. For banded iron formations, and I'll go into more detail in the next slide, but we see them kind of associated with the edges of the anomalies. And then for komatiites, there's some areas where they're mainly associated with the southern volcanic zone, but sort of seem to be in the same areas as the banded iron formations. The caveat for these is they're volcanic rocks, so once they're erupted, they can travel some distance, and there's speculation and modeling done on the viscosity of those lavas, but because they are ultramafic, they're probably lower viscosity and can travel relatively large distances. So you might be looking at These komatiites belonging to the La Motte-Vasson Formation near Val d'Or that are over an area of deeper moho. And in cases like that, it's hard to, we'd have to locate the eruptive source of those units. In terms of looking at banded iron formations, we also had a look at the work by Goodwin in 1973, where he classified iron formations into different facies, so oxide, sulfide, and carbonate. And so we digitized that map in order to compare it to the moho depth model, where we think these rift basins might be, in hopes that they could tell us something about the paleo-environmental conditions of the depositional basins in which these formed. And so the idea is that the carbonate and oxide facies, BIF, would be typical of shallow marine basins, probably along the margins, reflecting more oxidized environments, and the sulfide facies, BIF, reflecting deeper marine reducing basins. So we see an association. I'll highlight the northern volcanic zone as an example of those oxide facies, BIF, at the margins of the moho anomalies in association with the Casa Berardi fault zone. And we see the sulfide facies, BIF, more in the center of the anomalies. So that would be consistent with these being rift basins. And then other areas, for instance, like Noranda, having mainly sulfide facies, BIF. So this was kind of an interesting thing to look at as well. We also looked at mineral occurrence data, so not just the actual established deposits, but basically everything from showings and more developed. Specifically with VMS-associated commodities, looking for those centers of hydrothermal mineralization. And so this map is showing the zinc, copper, and lead occurrences, how they relate to the moho depth. So we see, again, large concentrations in Chibougamau, Matagami to Detour, Noranda, the Timmins, sort of Kidd Creek area. But we also see, again, just highlighting this sort of northeast-southwest oblique trending feature in the moho, we see concentrations between Cavalon and Demerayville, which is interesting. If we just look at, I love to make heat maps, so if we just look at heat maps of those occurrences, here is zinc, so this is just showing how spatially dense they are. We also see, and then the outlines showing a 38.5 kilometer moho depth contour, so outlining what we are considering our shallow moho anomalies. And we do see that they're mainly concentrated within or very close to those moho anomalies. Also looked at alteration, and to do that at the scale of the entire Abitibi, what we did is put together a whole rock lithogeochemistry database for mafic volcanic rocks, and then calculated some of the commonly used alteration indices, such as the chlorite, sericite, and Hashimoto, or more informally called the alteration index. So the original compilation had about 10,000 samples, and if you sort of plot this as a bubble plot where the sizes of the bubbles are proportional to the values of the alteration index, you can see that they're associated with the main mining camps and appear to be associated with the shallow moho areas. But it is a little bit biased because we are, the majority of the sample concentration is already within those areas. So to extend that database, and I apologize, this figure, I haven't fine-tuned it quite as much because I just finished compiling this, but I added 20,000 more samples to the database, so now there's about 30,000, and we can see trends a lot better. We see that there's just not as much of an alteration signature in the middle of the belt as there is in the north and southern volcanic zones that correspond with the moho anomalies. I'm going to try to blaze through this a little bit faster. We also looked at things like loss on ignition to get a sense of the amount of volatiles, which is just another kind of way to think about alteration, which showed very similar patterns. Another parameter that we looked at was the geochemistry of superficial sediments, so including till, lake sediments, and soil. And we looked at the concentrations of VMS pathfinder elements, so a few examples being arsenic, zinc, and copper. Looked at the concentrations of those elements. Again, we see similar patterns here looking at arsenic. This database has more than 600,000 samples, so it's really, I think this is a very powerful tool for looking at the regional scale. Again, we see similar patterns. We see very high arsenic concentrations within the MOHO anomalies, and not as much in the middle of the belt. Zinc, copper, and I'll just skip to some of the final things. We also looked at some geophysical data. So I took the residual total field aeromagnetic data and tried to identify zones of high magnetic mineral content, which would be correlated with VMS mineralization, banded iron formations, or mafic to ultramafic intrusions. And I did that by pulling out values within that data set that were above a certain threshold, so I used 230 nanoteslas. But what you see, again, we see horizons within the magnetic data that correspond to all of the anomalies we've seen in the other data. Final thing was looking at electromagnetics. So we looked at this data, compiled and pulled out electromagnetic conductors from this to try to identify sulfide-rich horizons, graphitic sediments, alteration, and fluid flow along major fault zones. So similar to the magnetics, we see kind of similar linear patterns in the data. So this is where we kind of get into the arm wavy part of the talk. Pulling all of this together, I think we have pretty good support from all of these data sets that these MOHO anomalies are real and likely represent Archean rifting. And so if we put this together with everything that we know and try to interpret this in terms of a mosaic of microplates like we see in modern regimes, we might get something like this. And this is something that Chris presented in his paper, but I kind of just took it a step further using, the outlines of actual structures. And again, this interesting northeast-southwest anomaly, Keaton might talk about it in his talk, but because it's so highly oblique to the main trend of all the fabric in the belt, with exception of the Lamarck fault, which I think is probably a very important structure, we're kind of interpreting this in terms of maybe a transtensional zone, so still associated with extension, but perhaps accommodating that southward transfer of rifting. So again, this is even more arm wavy, but I'm trying to find a modern analog to compare this to. One of my favorite places in the world is Iceland. Been there a few times. And this immediately reminded me of the situation that's occurring in Iceland, where you have the mid-Atlantic ridge being influenced by the Iceland mantle plume. That is expressed as a migration of rifting. It's continually jumping towards the mantle plume. And what you have expressed at the surface is the western volcanic zone dying out in activity, and that activity being taken up by the eastern volcanic zone, which is closer to the plume center. So I just plotted these two diagrams to show the ages of the volcanic rocks. And so in Iceland, perhaps there's something similar happening to what was happening in the Abitibi, and we're sort of in the middle of that process. And in the Abitibi, we've had that migration of rifting towards the south. And then the cool thing about this is it opens up some opportunities to think about what this sort of oblique boundary might have been. And in Iceland, it's a transtensional zone that accommodates that migration of rifting. You might be asking, why are there no northeast-southwest trending structures in the Abitibi, or at least only a couple of potential examples? Well, in Iceland, that transfer of extension is actually accommodated by rhydal shear sets that are subparallel to rifting. So you don't necessarily need one big transform fault to accommodate that motion. So I'll end with that, and happy to take any questions.